Okay, so in this lecture, first let me give this information, that is, suppose if a molecule, I'll represent molecule as M. If a molecule is exposed to some radiation having frequency nu, what will happen? First the molecule get excited. The molecule goes to excited state. Okay, this excited state molecule may undergo some chemical reaction or chemical change. Okay, it may undergo some chemical change, or it may undergo some physical change. Okay, the spectroscopy which concerned about the absorption of photon by molecule and goes to the excited state is what we call as absorption spectroscopy. Absorption spectroscopy. Suppose if you are interested only on the absorption spectroscopy, okay, so you can take UV visible absorption spectroscopy and you can study about the molecules. There is the other things also there to study. After excitation, right, this molecule may undergo chemical change with the molecule present in the ground state, or it can also undergo direct decomposition, right? We call those reactions as photochemical reactions. It's called photochemical reaction. So after excitation, the excited molecule may undergo photochemical reaction, right? Or sometime the excited molecule may undergo processes like vibrational relaxation. It may undergo vibrational relaxation, vibrational relaxation, vibrational relaxation, or internal conversion. It may undergo internal conversion, right? Or it may undergo intersystem crossing, or it may undergo I'll write here, okay, it's a continuation of this, or it may undergo photon emission, say fluorescence emission, or it may also undergo phosphorescence emission, right? So these are all processes associated with the physical change, right? All these processes, right, are collectively called as photophysical process. Okay, so it is up to you whether you are going to take only absorption spectroscopy or you are going to take emission spectroscopy. If you measure fluorescence or phosphorescence, we call that spectroscopy as emission spectroscopy in the case of electronic transition. Okay, so in ultraviolet, or if you expose a molecule to visible radiation or ultraviolet radiation, right, you can take either absorption spectroscopy or you can also take emission spectroscopy like fluorescence emission or phosphorescence emission. Okay, but in this lecture, first I am going to discuss the absorption spectroscopy, right? Electronic transition involving absorption, right? I am going to take only absorption spectroscopy, right, under UV visible spectroscopy, under electronic transition, right? We'll take like this, under electronic transition. So under electronic transition, we are going to follow only absorption spectroscopy first, first we'll see absorption spectroscopy, then as we go along we'll discuss the emissions like fluorescence and phosphorescence, right? Even in the photochemistry chapter you are going to learn, right, all these processes in a detailed manner. Here I'm just going to give some introductory idea about this. Okay, first let me finish off this absorption spectroscopy. Right, listen, in absorption spectroscopy, you know very well, transition takes place usually from stable ground electronic state. I wrote shortly, stable ground. Stable means electronic state as having minimum. Okay, electronic state, if it has minimum, it is called stable. Stable ground electronic state. Right? If molecule undergo transition from ground electronics state to a stable excited electronic state, okay, right? So usually in absorption spectroscopy, this transition will occur from stable ground electronic state to stable excited electronic state. Or sometime the molecule may undergo transition from stable ground electronic state to an unstable excited electronic state. This also may happen. Anyway, in absorption spectroscopy, transitions usually starts from the stable ground electronic states. Okay, right? So this is very, very important. Keep this in mind. So usually the transition starts from the stable ground electronic state of the molecule, right, in the case of absorption spectroscopy. Okay, then next important point here is that I have told you electronic states are represented with the potential curves, right? Once again, electronic states are represented with the potential curves. Now I will draw the vibrational and rotational structures associated with the electronic state. I am not going to draw the potential curve here, right? Because I like to convey some information here. So because of that, for time being, let us consider only the vibrational and rotational states associated with that. Very specifically vibrational state. I will take vibrational state. Now listen. See, assume that this is the ground electronic state. First let me draw ground electronic state. This is the lowest vibrational level associated with the ground electronic state. Then this is the next higher vibration level. Next higher vibration level. These are all vibrational levels associated with the ground electronic state. As we go above and above, the gap between vibration levels decreases. That and all you know, right? Assume that these are all vibrational states. Okay, assume that these are all vibrational states associated with the ground electronic states. So these are all vibrational states associated with the stable ground electronic state, right? And this is the lowest vibration level, V double prime equal to 0. We represent the vibrational levels associated with the ground electronic state, okay, we represent like this, that is V double prime 0, V double prime 1, like that. Okay, V double prime represent vibrational states associated with the ground electronic state. Okay, similarly we have the excited electronic states and the corresponding vibrational levels. Okay, I have told you all these informations in the last class, that each electronic state has set of vibrational levels and each electronic state has a set of rotational levels. So it goes like this, right? So these are all electronic that is vibrational states associated with the with the excited electronic state. It may be first excited electronic state or it may be second electronic state. Let me use the general term excited electronic state. So this is, let us assume this is stable, okay, stable excited electronic state, right? And these are all vibrational state which we represent as, it's a conventional representation, V prime equal to 0, then 1, 2, 3, 4, etc. Here also we have 1, 2, 3, 4, etc. Right? See, I have drawn, my aim is to show the vibrational structures, vibrational levels, right? So, time being, don't worry about the curve and all, potential curve, okay, potential curve definitely is there, right? So, without potential curve, I am just showing this, right? Now, listen, in the ground state, I'm sorry, at room temperature, right? I'll write here, at room temperature, we know at room temperature most of the molecules, at room temperature most of the molecules, almost all molecules we can say, right? Most of the molecules, in the sense almost all molecules, right? It actually depends upon the system, depends upon the molecule that you are handling, okay? But in general, at room temperature, most of the molecules are present, exist in ground electronic state. Very, very important. At room temperature, most of the molecules exist in the ground electronic state and ground vibrational state. Ground vibrational, not only ground electronic state. Okay, in ground electronic state, it present in ground vibrational state of the molecule. That is, see, this is the ground electronic state, right? In this, the molecules are present in the ground vibrational state. So molecules are usually present here, okay, at the room temperature. And populations in the higher vibration levels are almost negligible actually, right? Only in few cases you may have some molecules in the first excited vibrational state. Okay, let us not worry about that in the now. Okay, we will discuss that if it required. We will discuss that in the later case. Now, so almost all molecules are present in the ground vibrational state of the ground electronic state. So whenever absorption of photon takes place, suppose if molecule absorbs photon, transition takes place from the ground vibrational state of the ground electronic state to some vibrational state in the excited electronic state. Okay, see what I am trying to say. Listen, transition takes place from this electronic state to this electronic state. Okay, this is called 0 to 0 transition, or this electronic state to this electronic state, or this electronic state to, this vibration state, I'm very sorry, these are all vibrational states, okay, yeah, this vibrational state to this vibrational state. So the transitions, right, happens like this. Okay, like this we have many transitions. See this carefully. Listen, when you're considering absorption spectroscopy, right, absorption takes place from the ground vibrational state of the ground electronic state to an excited electronic state with the different vibrational states. Okay, so the vibrational states differ only in the excited electronic state. Right? We represent these transitions, right? How to represent these transitions? Yes, I'll write here. The absorption transition, right? Transitions, electronic transitions. I'll write like this. Electronic transitions in absorption spectroscopy. In absorption spectra, spectra are represented as how we represent? Listen, we represent like this, that is V prime within curve bracket, we represent V prime, V double prime. What is meant by that? See, this transition, say for example, this transition, first one, it is called the lowest vibration level is always 0, and the next vibration level, the excited state is 0. So this transition is called 0 to 0 transition. And the second transition is called 0 to 1 transition. This 0 represents ground vibrational state, and this 0 represents vibrational state of the excited electronic state. This is vibrational state of the ground electronic state. This is vibrational state of the excited electronic state. Okay. Then the next transition is called 0 to, we represent it as 2, 0. It is actually 0 to 2 transition. Then the next transition is called 3, 0, like that. Okay. So when electronic transition takes place, along with the electronic transition, many vibrational transition will occur, right? And along with many vibrational transition, many rotational transition also occur. I didn't show that, okay, but keep this in mind. Along with each vibrational transition, there are many number of rotational transition also occur. Okay, so the electronic spectrum, right, when electronic transition takes place from ground electronic state to some excited electronic state, several vibrational transitions, several rotational transitions occurs, and all these transitions, right, they are combined, they exist close together and appear as a band. Okay, so usually the electronic spectra, usually electronic transitions appears as band. Why? Because in each electronic transition there are several vibrational transition and several rotational transitions will occur. Okay, yeah. So and in this transition, in absorption spectroscopy, only the excited electronic state vibration levels are changing, right? Ground electronic state vibration level is always 0, almost always 0, whereas in the excited electronic state the vibration levels changes. Therefore we call this type of progression, right, that is 0 to 0, 2, 0, 1, 0, 2, 0, 3, 0, right? These each of these transition, vibrational transition, will give a line in the spectrum. All these lines merge together and form a band. Okay, and each line, suppose if you have sufficient resolution in your spectroscopy, in your instrument, then it is possible to measure all these vibrational lines. Okay, and each of these vibration lines which appear in the spectrum, right, is actually called a progression, right? Yeah, let me write here. Yeah, these transitions are called see here, the ground electronic state, right, has same vibration level in the transition, whereas in the exit electronic state vibration levels are different. Therefore these transitions, each of these transitions will produce a line, and those transitions are called V prime progression. Why? Because the change occurs only in V prime level, not in V double prime. Okay, so it is called V prime progression. V prime progression. Okay, let me discuss this in a detailed manner, right? So I have given that in an electronic transition at room temperature, this is the point I like to say. At room temperature, almost all molecules exist in the ground vibrational state of the ground electronic state. This is the point you should keep in mind. Okay, then the next one. Right. Yeah, listen. When we take electronic spectra, especially absorption spectra, right, not only absorption spectra as well as in emission spectra. In general, the vibrational changes that occurs in an electronic transition, right, leads to what we call as core structure. Okay, so let me take this one. See, vibrational changes, right, in an electronic transition, in an electronic transition, right, vibrational changes in an electronic transition leads to, okay, leads to core structure, core structure in the electronic spectra. Core structure in electronic spectra. Very, very important. Okay, in electronic transition, the vibrational changes 0 to 1, 0 to 2, 0 to 3, right? The vibrational changes in an electronic transition leads to closely spaced lines. Okay, those lines are called core structures. Even specifically, vibrational core structures. Sometimes people call it as vibrational core structures. Right, so keep this in mind. The transition that appear in an electronic spectra due to vibrational changes, right, those transitions will produce some lines in the spectrum, and those lines are called core structures. Okay, or simply we can say in an electronic transition, right, you will get electronic spectra. In that electronic spectra, if you get lines due to vibrational transition, those lines are called core structures. Okay, suppose I told you rotational changes also may occur. Rotational transition, right? Rotational changes in an electronic transition, in an electronic transition, right? Rotational changes in an electronic transition leads to fine structures. Leads to fine structures. Core structure, this is fine structure. Leads to fine structure in electronic spectra. Okay, and these fine structures are sometimes also called as rotational fine structures. Okay, this is vibrational core structures. See the spelling of coarse, C-O-A-R-S-E, core structures, and this is rotational fine structure. Okay, so these are all the conventional terms that we are using for rotational changes and vibrational changes that occur in an electronic transition. Okay, yeah. So first I am going to consider the vibrational core structures. Right? Once we finish this, then we'll discuss about rotational fine structures in an electronic spectra. Right? Keep this in mind. As I told you before, I am going to consider absorption spectroscopy first. Okay, we'll discuss about the fluorescence, phosphorescence and all, right, once we complete all these things. Okay, then the next point. So what I'm going to do now is about vibrational coarse structures, or simply core structures. Vibrational coarse, C-O-A-R-S-E, coarse structure. Vibrational core structure, right, of an electronic spectra, of an electronic spectra of an electronic spectra due to an electronic transition. Let me write like this: due to an electronic transition. see, vibrational core structure means the vibrational transitions that produce lines, okay, in the electronic spectra for a particular electronic transition. Okay, that is called core structure. Now, see, since we are considering only the vibrational transition in this case, let us assume that there is no rotational change, right? So I am going to consider electronic transition, right? I am going to consider electronic transitions, right, involve no change in rotational states. That is, the rotational state of the ground level and the rotational state of the excited level are same. Involve, right? Consider electronic transitions that involve, right? Electronic transitions that involve no or rotationless states. You can say like this. Involve rotational, right? Rotationless states. Very important. I am using a term, rotationless states. What does it mean by rotationless states? It means the rotation levels associated with the ground electronic, ground vibrational ground electronic state, and the rotation levels associated with the excited vibrational state of the excited electronic state. If these two are equal, we call that the transitions as rotationless transitions. Okay, so in this case you can omit, or you need not consider, right, the rotational transitions in this case. Okay, yeah. So under this situation we can write that using the Born-Oppenheimer approximation, we can write the nuclear part of the wave function as into two parts, that is electronic and vibrational alone. Okay, see, under this assumption, right, we can write the total wave function, right? Let us not worry about translation and other things, right? I'll consider only this, right? So the total wave function is actually approximately equal to, it is not exactly equal, it is approximately equal to the electronic wave function, right, and the vibrational wave function. Let me write VSI vib, right? Under this assumption that if the transition takes place, right, with the rotationless states means, listen, the J double prime and J prime are equal. Okay, that's the meaning for rotationless states, right? Under this assumption, you need not consider rotational wave function here. So I am going to consider only this. That is, total wave function consists of the electronic wave function and the vibrational wave function, right? So the transition that going to appear due to these two are usually called as vibronic transitions. So I am going to very specifically consider vibronic transition, right? The lines that appear due to vibronic transitions are called actually core structures, simple. Okay, yeah. So psi total is approximately equal to psi electronic and psi vibrational, right? Now what I am going to do is I am going to derive the selection rule, right, for the vibrational core structure, right, in the absorption spectra, right? Yeah. So I am going to consider only absorption spectra first. I told you in the beginning, right? Keep that in mind. Now, so what is the selection rule? What is the selection rule under vibronic transition? I have already discussed about general selection rule, but now I am going to give the selection rule for vibronic transition alone, right? Yeah. So in this case, we can write, you know very well, selection rule means we should consider transition moment integral. transition moment integral, right? You all know that for any transition, this transition moment integral should be not equal to 0. So we can write simply this as I'll write in the bracket notation proposed by Dirac, that is the bra of excited vibrational wave function, excited wave function, excited total wave function, then dipole operator, then ground state wave function. Okay, this gives you the transition moment integral. Okay, yeah, this is actually called bracket notation, right? It is a short form of writing the integral that you know already. Now what I'm going to do, before substituting the wave functions and other part, let me give some idea, some information on this dipole operator. Listen, in the case of electronic spectra, when a molecule, suppose assume that this is the molecule, right? Initially in this molecule, the electron densities may be, assume that the electron densities are uniformly distributed. Let us assume. If the molecule absorb a photon, right? If the molecule absorb a photon, what will happen in the molecule, right? The electron distribution will occur. Electronic distribution will occur. So you may have, suppose you may have a situation where electron density will be more in one side and less in the other side. Okay, the electron density become more in one side, gets partial negative charge, and the electron density which is less in the other part, okay, you will get partial positive charge. This leads to a dipole moment. Okay, this dipole moment is due to electrons. Okay, so absorption of photon, very specifically UV visible radiation. UV visible radiation brings change in the electron distribution of the molecule. So whenever molecule absorb UV visible photons, right? Let me use the term like this. Then electron distribution will occur, right? Which leads to a dipole moment of the molecule, right? This dipole moment due to electron, right, is a very important quantity in the case of electronic transition. Not only that, see the nuclei, right? We have several nuclei, right? Several nuclei, right? When the nuclei which carry positive charge, they also give some kind of dipole moment, right? Because when electron distribution occurs and there may be change in the bond length, right? Because of that, the dipole moment may arise due to the nuclear positions, right? So this dipole moment operator, okay, so the point I like to say here is when molecule absorb UV visible photon, okay, it will leads to a dipole moment. Suppose if molecule already has dipole moment, the dipole moment will alter. If the molecule does not possess any dipole moment, so suppose if it is a homodiatomic molecule, right? If it is a homodiatomic molecule, then when the molecule absorb photon, yes, you will get dipole moment due to the electron distribution and nuclear positions. So the point is here is that the dipole moment operator actually made up of two quantities. One, dipole moment due to electronic arrangements. Okay, the other one, dipole moment due to nuclear positions. Dipole moment due to nuclear positions, dipole moment due to electron arrangement. Okay, so electron dipole moment, nuclear dipole moment, both will come. Okay, this is very, very important. Now let us consider this integral, the transition moment integral. Let me write here. So transition moment integral can be written as transition moment integral equal to integral of in the place of excited electronic state, I'll write the wave function for electronic wave function. Let me write electronic wave function as ES. Actually, electronic wave function as the spatial part and the spin part. Okay, so I am considering both psi e means spatial part, psi s means spin part. So this is actually spin orbital, okay, spin orbital into vibrational part of the wave function, psi vibration, psi v. Since these two are excited state, right, I will put single prime, okay, psi e s single prime, psi v single prime indicate excited state. Then in the dipole operator I will put electron dipole moment due to electron arrangement and dipole moment due to nuclei arrangement, okay, arrangement of nuclei. Then in the place of ground state wave function I will put psi e double prime s double prime into psi v double prime. I will put like this. Okay, this is actually an integral that you know, so I'm not going to discuss what is Dirac notation and all, right. Now this integral, see here we have positive sign, so this integral can be separated into two parts. Yes, I can separate this as psi e prime s prime into psi v prime mu e dipole electron dipole moment operator into psi e double prime s double prime into psi v double prime, okay. And another integral is this, that is integral psi e prime s prime into psi v prime mu n, then psi e double prime s double prime psi v double prime, okay. So I have separated this into two integrals, okay. Now let us discuss about this one first. See, this operator, it does not contain any electronic coordinates. See, this operator does not contain any electronic coordinates, so it operates only on the nuclear wave function, okay. It operates only on the vibrational part, because this wave function has electronic coordinate. This wave function has only electronic coordinate, okay. Therefore this operator does not operate on this, because this operator does not contain electronic coordinate, so it operates only on the only on this wave function which depends on nuclear coordinate, okay. Similarly here if you see these two wave functions, this wave function does not contain, it is a vibrational wave function, it does not contain electronic coordinates. Therefore this operator does not operate on this function. Therefore I can separate this further as, you can separate this further as, listen, I'll take the here this operator operates only on this wave function, so I am going to separate this psi v and psi v prime, okay, in a separate integral, okay. I'll write like this, psi v prime psi v double prime. Let me separate that first. Then the next integral is psi e prime s prime into mu e operator, then psi e double prime s double prime. This is the first integral I have separated. Then plus the second integral. What is the second integral we have? This one. In this case I told you this operator operates only on the vibrational function, so I can separate the electronic states. So let me separate the electronic states. Psi e prime s prime psi e double prime s double prime, okay, and here we have psi v prime mu n operator psi v double prime, okay. Actually it should represent this as black, okay, no problem. Yeah, now so I have separated it. Now listen, for a given molecule, two different electronic states having different energy, okay. Suppose in a molecule, suppose I have an electronic state here and another electronic state here, so these two electronic states have different energy value. Two different electronic states and their wave functions must be orthogonal for a molecule, okay. So in a given molecule, the wave function associated with the excited electronic state, that is this, and the wave function associated with the ground electronic state, that is this one, right. Two wave functions of a molecule, if they have different energy, then they must be orthogonal to each other. Okay, so these two wave functions, these electronic wave functions are orthogonal, therefore this becomes equal to 0. So this integral value becomes 0. If this is 0, you need not worry about this. So the entire thing becomes 0. Therefore the above integral becomes, that is the transition moment integral, therefore it will become equal to, so now the transition integral has only these two parts, that is psi v prime, psi v double prime. Okay, and here also listen, this spin function we can separate. Suppose if there is no spin orbit coupling, let us assume, right? Right, I'll write once, then I'll write in the next page. Yeah. Psi e prime s prime mu e operator psi e double prime s double prime. Okay, we left with this. Then suppose if there is no spin orbit coupling, right? If spin orbit coupling is negligible, right, or absent, if spin orbit coupling is negligible, then this wave function can be separated into two parts. Okay, let me write in the next page. So in this case, the wave function that is then, right, yeah, is negligible, then we can separate this psi es, right, that is a spin orbital. Right? This spin orbital function can be separated into spatial function of the electronic part and the spin function of the system. Right? So we have separated the electronic and spin part. Right? If the spin orbit coupling is negligible or absent. Okay. So under this situation, right, we can write the transition moment integral. Therefore, the transition moment integral can be written as integral psi v prime psi v double prime, okay, into I can separate the spin part, right? So we can separate the spin part as spin part. Let me write psi s prime psi s double prime, because the operator, this operator, electronic operator, this operator does not operate on spin part of the wave function. Therefore, you will get spin part here, you will get spin part here. Those two spin part can be taken together as out. Okay, you can take those things together. Okay, therefore the thing that is left with is psi e prime electronic dipole moment operator into psi e double prime. Okay, you'll left with this, right? Yeah. Suppose if any one of this becomes 0, then the transition moment integral becomes 0. If transition moment integral is 0, the transition does not appear in the spectrum. So the point is very, very clear that all these integrals should be not equal to 0. Okay, and here this integral is what we called as vibrational overlap integral, right? Yeah, this integral is called vibrational overlap integral. Let me write here. It is called vibrational overlap integral. Okay, vibrational overlap integral, and here there is no restriction on the values of v prime and v double prime, right? Actually, any transitions are allowed in this case. Okay, there is no restriction. And for this integral to be not equal to 0, right, the second integral, we will discuss about this integral later. Let me discuss this one first. Okay, the second integral, that is psi s prime and psi s double prime, okay, the spin part, this is not equal to 0 only if transition only if transition takes place, only if transition occurs from singlet to singlet, if transition takes place from singlet to singlet, or transition takes place from triplet to triplet, right? If there is no spin orbit coupling, then the selection rule is this, that is singlet to singlet is allowed, triplet to triplet is allowed. Okay, and only under this case the value of the integral is not equal to 0. If the integral value is not equal to 0, then transition moment integral also not equal to 0. Okay, then this integral, right, must also be not equal to 0, right? So psi e prime mu electronic dipole moment psi e double prime, this integral should also be not equal to 0. For this integral not to be not equal to 0, yes, we have orbital selection rules. We will have orbital selection rules that we already discussed. Orbital selection rules. Okay, you will get transition like sigma to sigma, right? Several transitions will come. It comes under orbital selection rule, right? We have already discussed about that. Gered to gered, gered to ungered are allowed, plus to plus allowed, right? Those things we discussed already, right? It's called orbital selection rule, right? Now our focus is on this, that is vibrational overlap integral. Listen, the square of this integral, right? This vibrational integral, right? So you take the square of the magnitude of that integral. The square of the magnitude of that integral is what we call as Frank-Condon over factor. Okay, so what is Frank-Condon factor? Frank-Condon factor. Frank-Condon factor. What is Frank-Condon factor? Frank-Condon factor, we usually represent Frank-Condon factor with the symbol S. S is equal to, right, magnitude of square of the magnitude of this overlap integral, that is psi v single prime psi v double prime. Okay, this is called Frank-Condon factor, right? Why this is very, very important? Because the transition intensity, okay, in an electronic transition, many vibrational transition takes place. The intensity of each vibrational transition, right, actually decided by the Frank-Condon factor. Okay, yes, it is also decided by Boltzmann factor or Boltzmann distribution, but I told you in the beginning, at room temperature most of the molecule, almost all molecule present in the ground vibrational state. Therefore you need not worry about Boltzmann distribution in this case. So in this case, in the absorption spectra, right, the intensity, right, specifically depends on the Frank-Condon factor. Higher the value of Frank-Condon factor, right, higher the value of Frank-Condon factor, higher will be the intensity of the transition. Okay, so intensity of the transition V prime V double prime, intensity of the transition, right, intensity of the transition V prime comma V double prime. You know very well what is the meaning for this. The meaning is the transition takes place from V double prime to V prime. Okay, right, the ground electronic state of the ground vibrational state to an excited electronic state having some vibrational state. The intensity of this transition, right, depends on or is proportional to, is directly proportional to the value of the Frank-Condon factor. As Frank-Condon factor value increases, right, intensity of the transition also increases. Okay, yeah. So we have discussed some basic ideas on vibrational coarse structures. Okay, I stop here. In the next class, let me introduce what is Frank-Condon principle and the other informations. Okay, yeah, I stop here.